So I guess we're ready to go. Okay, so the second talk in this session is going to be by Pooya Ronagh, who's going to be telling us about mixed integer programming on a Bosonic quantum computer. So please.
Thanks so much. Yeah, I should also thank the organizers for this nice event and for having us here in Bristol. So yeah, my name is Pooya. I'll talk about mixed integer programming on a Bosonic quantum computer. And this is really, mostly just the motivation for talking about a different flavor of adiabatic quantum computation, specifically with continuous variable quantum information. This is a joint work with Farhad Khosravi and Arthur Scher, both from 1QBit. All right, so just to motivate things, I've been working for a few years on solving practical problems with quantum computation, and especially in machine learning and optimization. And these weren't my background, so I've learned all of these things through the years that I was working on quantum computing. And so one of the problems that exists is that continuous variables are represented in classical computers quite easily. You do float point representation. You have a lot of bits in your quantum memory, in your classical memory, and then you can think about fixed point and float point representations. And it's quite easy to build large data structures from these things, and then do arithmetic on real numbers and calculate polynomials and non-polynomials transcendental functions on them. In circuit model quantum algorithms, when we talk about the circuits themselves, they look pretty easy. They look pretty simple. But then when you look at resource estimations from quantum algorithms, you end up with these astronomical numbers of gates and qubits you have to use. And the reason is really all that complication goes into these boxes that are the quantum oracles that you have to actually construct for different problems. And that's where all of these resources are being spent on. So this is not a complexity theoretic problem. If you have, I guess there's this folklore result that I didn't know that it's actually, I guess, written in Nielsen Trang as well, but I was taking this statement from a paper, from this last paper that I cited from Microsoft group, that if you have a circuit, if you have a computable classical function, then you can just build the oracle from it with no overhead, like similar, or in linear resources, number of quantum gates you would have to use would be in the same order of the number of classical gates you would have to use. And then you can do queries to it and then do like amplitude amplification or phase estimation on it. So there is no complexity theoretic issue here, but then when you actually go and do resource estimations and things like Shor's algorithm and other problems, then you will end up with really, really big numbers of gates that you would have to use. So this is a paper also from the Microsoft group back a few years ago, that they were trying to look at the ways that people optimized classical arithmetic when they were building like arithmetic logical units in classical computing, and use those methods to come up with good algorithms, good quantum circuits to build like transcendental functions. So then you probably would you will end up wanting to compute. So these are a couple of rows of a larger table that they have, but as you see, the number of Toffoli gates that you would have to use to calculate a tangent hyperbolic or exponential of a real number, they get to the 10 to the 4, 10 to the 5 number of magic states that, for example, you would have to use. Okay, so these are logical resources, and then you have like the number of physical qubits and physical gates that you would have to use is just really large. Okay, so but if you want to do useful things before being able to do those large numbers, those large oracles, then we will have to somehow get rid of or optimize our arithmetic in a way. And there are lots of papers on trying to kind of avoid this problem. So for example, in amplitude amplification, you usually want to build a phase oracle, and then to do arithmetic in the phase of your quantum state, then maybe you would want to do arithmetic directly on the phase, and there are ideas of how to do that with quantum Fourier transform or this quantum amplitude arithmetic, papers that I learned about as I was working on this project. And there are also papers that try to kind of completely avoid doing arithmetic and then restate the problem of doing arithmetic as a state preparation problem, so that they get some saving from not having to do those really large resource circuits. Okay, so then even when you're actually working on optimization problems where you do things as ground state preparation, then you have a different problem again with the precision of the arithmetic you would have to do. And this is not even actually just for quantum, quantum methods for optimization. So if you look at this Markov chain Monte Carlo, simulated annealing, parallel tempering, I don't know, quantum annealing, all these different Ising machines that people have built over years. And then, QAOA, VQE, shorterized, discretized adiabatic evolution, all of these schemes are kind of a heuristic for preparing a ground state to perform optimization. And when you do something like this, then you have to take your continuous data structures, you have to discretize them. But if you discretize them using binary representation, then you're really limited to a fixed point representation in a way. And then what that means is that you have these representations that are like of the form 2 to the I xi. So that means that the coefficients in front of your variables are growing exponentially. So some of them are exponentially larger than the others. And then you have this Hamiltonian that you're trying to optimize where some of the terms are exponentially have like coefficients that are exponentially larger than the others. And you're not actually like all of those smaller terms are being completely suppressed. And you're solving an optimization problem that has nothing to do with the original problem you started from. Okay, so I wrote this other paper a few years ago on trying to find better encoding than like the usual binary representation is resource efficient because it uses logarithmically many bits or logarithmically many qubits. But then maybe you would want to do something like unary encoding, which is going to use a lot more qubits. But then that might actually make the landscape of your optimization problem more well behaved for all these optimization schemes. And so then we were asking, like, is there something between unary, which is not resource efficient, and then binary, which is not good for the landscape? And then we were coming up with this bounded encoding, bounded integer encoding. And then you see on the, it doesn't quite work. Yeah, you see like the line that is going straight up is from the binary representation. So those are the time to solution if you were using binary representation in your optimization problem. And then the two lines, the two curves, the one that is kind of flat is the unary encoding. So it has a bad prefactor, but the time to solution scaling is really good. And the blue one was this bounded encoding. Okay, so these are all kind of motivational comments on what I'm going to actually talk about is that, so we're thinking that, can we actually just find the right physics for these problems so that we avoid just doing things in a digital way. Quantum mechanics, when you learn it, you use wave functions and you have momentum and position, and these are continuous Hamiltonian. So I think that actually gives us an opportunity of finding a good solution. So when you work with bosonic statistics, then you have, you start with a continuous Hilbert space in 3 dimensions, for example, then you create this graded Fock space, which is each of the Fock levels correspond to the number of photons in your Hilbert space, and then you have this grading that comes with this annihilation and creation operators. So then the photon number operator, which is A dagger A, that is like this decomposition is an eigen decomposition of that operator. So you naturally have an operator that has discrete spectrum, but then you actually started from position and momentum, which have continuous spectra. And that's really nice because then I have 3 operators, so position, momentum, and the number operator, and these are all non-commuting with each other. And that's all the stuff you need to be able to build an adiabatic scheme, right? So what we want to do is to start with a position operator and then build a mixing Hamiltonian out of the position operator. And then because I want to do mixed integer programming where I want to both represent continuous numbers and discrete integer numbers, then I will take the position, I'll start with a mixing in momentum, and then I'll use the position operator and the number operator to represent the Hamiltonian that I want to find the ground state for. Okay, so then if you have a photonic system that realizes the scheme, then you would want to do something like photon number resolving detectors for measuring the optimal integer variables, and then you want to do something like homodyne detection for the continuous variables. Okay, so really the question is there might be different ways of finding ground state of a Hamiltonian. I'm just gonna for these examples that I'll show, I'll just use an adiabatic evolution. I'll use the simplest adiabatic evolution that starts from this mixing Hamiltonian that I was talking about, and then it just does a linear combination all the way to the problem Hamiltonian that is encoding the optimization problem. So the mixing Hamiltonian we need to use, as I say, it has to be non-commuting with the problem Hamiltonian, and then it has to have a ground state that I can easily prepare, so that when I do this adiabatic scheme, I already start from ground state and I evolve slowly enough so that I stay in the ground state. So for example, you can think about squeeze states along the position axis, and those would be states like these tensor product states of this form, of this simple form, which you can build using phase shifters, for example. But this is infinitely squeezed, and you need infinite energy for that. So you would probably want to do something like a finite squeezing. So these are coherent states that are squeezed along the position axis, but they're centered around those P01 to P0n given n quantum modes for the problem that I'm trying to solve. Okay, so these are states that we can generate, and that's the Wigner representation of that state. And then we want to do that adiabatic evolution. So I'll start with a simple example. So in optimization, feasibility problems and optimization problems are usually in classical optimization considered to be similar, but because here we don't have access to a lot of flexibility that classical optimization community has, they're not really similar problems. But I'll start with this feasibility problem. I just want to solve this really simple equation. So you're looking for solutions of n1 plus n2 equal 5, where n1 and n2 are both non-negative integers. So you're looking for 0, 5, 1, 4, 2, 3, 3, 2. And so I do this adiabatic evolution that I'm showing there, and so numerically we look at how things would evolve. And so you start with the vacuums, like squeezed vacuum state, and then you want to do this adiabatic evolution. And as you do the adiabatic evolution, you see that the correct states that represent those 5 and 6 integer solutions, they kind of get amplified through the adiabatic evolution. Okay, so there are other advantages to having so now I have this parameter I can change. I can change the squeezing, and I can change the center of that coherent state that I start from. And unlike in QAUA or adiabatic ground state preparation, you have like a continuum of mixing Hamiltonians to choose from, which is really nice because it gives you a lot of advantage. So on one hand, the fact that I have to use finite squeezing, usually in CVQC, it corresponds to you're thinking about an algorithm that needs infinitely squeezed states. But here, if you have finitely squeezed states, then that just means that if I have this feasible domain, I can change this parameter, and it literally sheds light on different parts of the feasible domain. So you can think about variationally focusing on different parts of the feasible domain. And then again, the fact that I have these continuous knobs to turn helps me do things that usually are considered as challenges for adiabatic optimization. For example, in the adiabatic theorem, you're promised that you will have a lot of overlap with the ground state. But if you have degenerate ground states, it's not guaranteed that you will be able to observe all those ground states. It's definitely not guaranteed that you will observe them with equal probabilities. So this is called biased sampling or unfair sampling in adiabatic optimization. And so if we change this parameter, like either variationally or something about the structure of the problem you're solving, then you will see that it amounts to just like, as I said, amplifying different parts of that feasible region. So this feasible region for different choices of that initial mixing Hamiltonian, you will be basically finding different parts of this ground state. Okay, so now I'll give you a few examples to show why it's hopefully it's useful to do something like this. So maximum click problem is a problem that has been studied a lot with adiabatic optimization and QAOA. And usually the way you write it in terms of these binary variables. So the binary variables represent whether a node in your graph is going to be participating in the click you're constructing or not. And here I can't just use non-negative integers, I have to use binary variables. So then I have to penalize higher photon numbers. And then I will add a term like this to the Hamiltonian. And as you will see, so in this example, I have two maximum clicks. The two triangles are both maximum clicks for this simple graph. They're both being amplified through the adiabatic evolution. But if you look at the green line, that one is not a feasible one. So even though I was trying to penalize higher photon numbers, I wasn't completely successful at doing that. But then because I have continuous variables, I can do something totally different. So it turns out there is a continuous formulation. Even though maximum click problem is a combinatorial optimization problem, but it's a discrete optimization problem, you can write a completely continuous formulation for it using the same adjacency matrix for the same graph. But then adding this simplex condition of summation of xi equal to 1. And this is a famous theorem from Motzkin and Strauss from 1960s. And so it turns out that solving this global non-convex optimization problem would actually let you find the clicks in this combinatorial optimization scheme. So we tried to solve this continuous formulation now. And then now you see that I can actually, so the bias is different. I don't see the orange click anymore as frequently, but I do have, the scheme is still working and finding the ground state. Okay, so a problem that has been studied a lot in the context of AQC and QAOA is knapsack problems. And usually the papers, and I'm sure there's a lot more that I don't know about. I just cited a couple of papers that I've seen talks on. In these, there are lots of ideas to make things work in practice, and lots of nice heuristics applied, but it kind of doesn't work really well. And then even there, they don't actually solve the knapsack problem that you care about in operations research. They solve the binary version of the knapsack. So the knapsack problem is asking you to find, like the largest, the most number of items you can put in the knapsack, given some capacity constraint on the knapsack, and then you have some weights for the items. But in a real world scenario, like if you have a cargo and you want to fill the cargo as efficiently as possible, and you're like getting items from a manufacturer, you don't have a single phone made by the factory. They have phone as a type, and then they build many phones, and then you're supposed to select how many of each type you want. So it's actually an integer optimization problem. It's not a binary decision, and these papers don't even consider this actual real world situation. So the nice thing is, now with this scheme, you can solve the actual integer knapsack problem. So I'm just showing this simple example, and there's no need for the weights to be small. There's no need for them to be integer. So all those complications go away if you can build a photonic, for example, system that does this. Okay, so I talked about mixed integer problems as the title of the talk, but I didn't show you a mixed integer problem. So problems like compressed sensing, like lots of problems in signal processing, you might actually be solving for example, inverse problem that itself is easy to solve. It's a convex problem, but the difficulty comes from you're looking for solutions that are sparse. So structure comes from sparsity. If you just solve your inverse problem without adding sparsity conditions, you get something that looks like just noise. But if you want to have things that have actual patterns in them, in lots of signal processing situations, then you need some sparsity conditions. So you're trying to solve optimization problems with certain number of constraints. They could be linear, they could be nonlinear, but then you have this hard constraint that is asking for a lot of zeros in that solution. And that's what I'm showing with this cardinality, the zero norm of the solution has to be bound. So for example, in portfolio optimization, also you're not trying to invest in, you don't want to track 400 stocks. You want to read, news on very few stocks that you actually want to track and make good decisions on them. So you have like, maybe you have like 500 stocks that you could select from, but the portfolio you actually want to build, you really want to have only 20, 30 of them in it. And the fact that you have this sparsity is making things really difficult. And you know, people have tried to attack this problem again using, like, you know, in the quantum annealing community, and it kind of doesn't really work well. And so the way you can convert it to a mixed integer problem is that you take this sparsity constraint. So in this example, you know, you take this, so I'm looking for solutions. So these two give me a convex problem to solve. Yeah, so without the cardinality constraint, I'm just looking for an optimal point in this simplex, which is a convex region, and the objective function is convex. But then I'm asking for solutions that only have at most 2 non-zero elements in them. And then if I only want 2 non-zero, then I'm looking at the boundary of this simplex, which is shown with the red. So this is the one skeleton of this simplex, and that one skeleton is non-convex, and then that's what makes the optimization problem hard. But then, you know, you can, so now what I do is that I assign a binary variable to whether any of those xi's were 0 or not. And then I get 3 continuous and 3 binary variables. So I get this mixed integer formulation, and then I can now solve this mixed integer formulation with the same. Okay, so there are lots of good questions now to ask. So all these problems, examples that I show are very, very small because we're trying to truncate a Fock space to like 4 or 5 levels. And then we could only at most like simulate 4 to 6 Q modes with it. And even there, like the probability amplitudes don't add up to 1 because there's a lot of leakage from the wave function. And it was really difficult to do things numerically. So I think one problem with even studying these methods is going to be that it's way harder to study them than like qubit-based QAOA. And, you know, if we want to build something like this, then, you know, in quantum control problems, we try to solve large Schrodinger equations with, you know, if you're just simulating a transmon, you at most like do it as a qubit so that you also take into account the leakage from your qubit bases. But here, like if you want to do like, you know, non-trivial gates and control them, then you have to do some really large simulations. So there's a problem with simulation. The gates that you would have to build to be able to do something like this are these unitaries that involve 2 photon numbers from 2 Q modes. So they're called like carrier gates and cross-carrier gates. And as far as I understand, these are not, like, they're proposals of how to build them, but they're not really good gates that are built yet. And then the other problem is this is an adiabatic scheme, so you have to go slow. And as you scale up the problem, you have to be able to do things, you know, longer than your noise sources allow you. And then you would want to maybe discretize and then do error correction. But then we don't know if we can do error correction in these bosonic systems. So you guys probably have heard, well, in this conference, you saw GKP states. GKP states are stabilizer codes that are, you know, these days are commonly being used to build good qubits, but not used for CDQC. And then I've found a couple of papers from so last year, like 2 years ago, there was this oscillator to many oscillator encoding, which is trying to protect one oscillator with redundancy. And then there was a QIP talk this year that was showing that these oscillator to oscillator codes don't admit a threshold. So that's a negative result for being able to do error correction, maybe. There are lots of assumptions on how the noise model looks on this, and maybe things are, you know, are going to evolve. And then there's no good adiabatic theorem again for these continuous spectra. So I've seen one paper, like, you know, we don't have a gap because it's continuous. So usually you explain the complexity of your adiabatic scheme using, like, you know, how fast the gap is closing in the adiabatic evolution. But, you know, here you have continuous spectra. And then I've only found one paper that is only looking at when, like, all the instantaneous Hamiltonians have continuous spectra. But in the scheme that I was showing, I was starting from continuous spectrum and I was finishing with a discrete spectrum. So you don't actually have a completely discrete spectrum, and then you don't have a notion of gap. But, you know, this paper at least has developed the theory enough to show that if you go slow enough, then you're staying close to the ground state. So that is known, but, you know, how do you, like, we need more theory to be able to even, like, talk about complexity of this scheme. Okay, so to wrap up, so CBQC has been proposed as a way of doing universal computation in the sense of realizing all sorts of unitaries in quantum modes. And then there's like boson sampling, which is just using the Fock space and the photon numbers. And there wasn't a way of using both of them to build a good quantum algorithm. And so this is what we are trying to do here. I should also say that this paper from a Kim Kem's group was looking at like a NIST CBQC counterpart for NIST counterpart for CBQC, but they weren't really exploring what are the advantages of doing things like mixed integer programming. This gives us a lot of merit because the representation of data structures are becoming simpler, and handling constraints becomes simpler as it is in the classical optimization textbooks, because now you have access to continuous variables and you can do relaxations as optimization theorists do. Like now we can also solve actually global non-convex problems which don't even have good classical techniques for them. So even the NP problems like usually is defined as, if I give you a solution, you have a polynomial time method of checking that the solution is correct. But if you just look at a quadratic function, non-convex function, and if I give you a point of it, even checking the forget global optimal, even checking the local optimality of that point itself, checking it is NP hard. So these are really, really hard optimization problems, and then there are no good, like there's nothing like branch and bound, branch and cut. These techniques are all for discrete optimization problems. So there's a lot of opportunity to do a lot better than what can be done classically. And the fact that we have these flexible choices of Hamiltonians are useful for machine learning applications. For example, you can do fair sampling, and fair sampling gives you Gibbs states in the 0 temperature, and things can be very useful. So I probably asked more questions than answering questions, but I hope I motivated those questions, and I can take any questions you guys have.
Thank you very much for that really nice talk. Indeed, are there any questions? No, I guess I have one. So I guess I'm just wondering about the sort of underlying theory of adiabatic quantum computation with these sort of bosonic systems, particularly variable systems. Is the theory basically the same? Like, do you need to develop some new results, or is it something you can take from it?
Yeah. So I only found this one paper that looks at when the spectrum is completely continuous, and there they show that you have to walk with 1 over precision kind of factor to stay close to the ground state. But I think that it wasn't enough for me to, like, for example, the results of 1D Ising model is a gap system, and that's why you can efficiently find the ground state for it. And that result doesn't give us enough tools to do an analysis like this. I think that the result, as I understood from that paper, is that it's like morally it's true that you just have to be slow enough so that you stay close to ground state, but I think it wasn't giving us enough to show that, like, what is the success probability of an optimization scheme. So I think like all of this has to be built for continuous systems.
So I guess that's an opportunity, right?
A lot, yeah, definitely.
Any other questions? Okay, well, if not, I guess we'll go to the coffee break after thanking the speaker again.